Welcome to the Unit 6 guided practice for your test remediation packet. We're going to start by going over a few of the academic vocabulary. You need to memorize these, and we're going to start by just defining some of them. The first one is covalent bond. That is a chemical bond between two or more atoms that results from the sharing of electron. In general, this is a non-metal bond. A polar covalent bond, there is unequal sharing of electrons in that covalent bond. A non-polar covalent, there is equal sharing of electrons in a covalent bond. A molecule is defined as two or more atoms that are chemically bonded together, generally referring to covalently bonded atoms. Metallic bonding, this is a bond between two metals that results in the delocalization of electrons. Molecular formula. A molecular formula represents the number and type of atoms. Empirical formula. That is the simplest whole number ratio of atoms in a molecule. And then lastly, our percent composition is the percent of total mass of a compound.
Difficult it's going to be for you to kind of separate out multiple different substances. So whenever you have a covalent bond, they tend to have relatively low melting points. Not only do they have relatively low melting points, but based on the melting point, you can usually tell whether it's polar or nonpolar. Nonpolar substances will have the lowest melting points possible. It's the same thing with lattice energy whenever you're trying to separate these things, although lattice energy tends to not really occur for covalent compounds. So now it says, what determines if a bond is polar? Well, you're really looking at two things whenever you have trying to determine if one thing if a bond is polar, and that's going to be the electronegativity. So you look at the electronegativity difference, and if you have an electronegativity difference between greater than about zero point 0.5, if it's greater than about zero point 0.5, it's going to be considered a polar bond. Anything that's less than that, although there is a little bit of polarity, it is still considered to be nonpolar at that point if it's less than zero point 0.5. All right, so the other thing that you have to look at whenever you're trying to determine if something overall is polar or nonpolar is you have to look for symmetry. Because if you have bonds that are polar, but those bonds go in opposite directions, then they can cancel each other out and the entire molecule can be considered nonpolar. So make sure you're looking for symmetry as well. So give an example of a nonpolar covalent bond between two different atoms. So for example, if you were to look at your table of electronegativities, you'd be looking for two substances that would form very, very similar electronegativity values. And the most common one that you tend to see is carbon bonded with hydrogen. And the reason for that is carbon is actually has a value of 2.5 and hydrogen has a value of 2.1. So when you subtract those two values, the electronegativity difference is about 0.4, which falls into our range of nonpolar. So now, for number 5, it wants us to determine if the bonds are polar or nonpolar. So the first one I can say is nonpolar. Okay, I looked at the electronegativity difference. For the next one, I can say that it's polar. Okay, the electronegativity difference there is going to be 0. And then for the last two, this one's right on the border. It tends to be classified as a polar because it's right there. And then for the last one, you tend to have, once again, it's going to be nonpolar. So remember to look at the electronegativity differences for those, so make sure you can answer those correctly. Next, we're going to write and name chemical or covalent compounds. So now remember, when we're writing the name of covalent compounds, we do need to include dis and tris and any sort of prefix to indicate the number of atoms that are present. So for example, I have 2 nitrogens, which means I would call it dinitrogen. Okay, dinitrogen indicates that there's 2 nitrogens at this point. And then I have 5 oxygens, so I'd write pentoxide. And now if you put pentaoxide, that'd probably be okay with your teacher, but generally when you don't have 2 vowels that are going to be next to each other. Okay, now for the next one, you should be able to figure out that it is tricarbon, and that it is going to be heptahydride. And the last one would be octahydrogen. sulfur monoxide, octosulfur monoxide. Okay, so now you're going to do the exact same thing, but in reverse. So now you want to be able to take the chemical formulas that are, or you want to write the chemical formulas given the names that are present. So when you look at these, you would say, okay, sulfur trioxide. So the fact that there's just a sulfur indicates that there's just an S, and the fact that it's trioxide means that there are 3 oxygens. And some people would look at that and they would say, oh, that's sulfite from the last unit, but it's not because there is no charge. So since there's no charge, it's just sulfur trioxide. So now triphosphorus hexoxide. So I would say, okay, P3O6, and you should be able to figure out the last one. It would be something like this. Okay. Now it wants me to draw Lewis structures for the following. And remember, anytime you see Lewis, that means we're talking about valence electrons. So whenever I draw the Lewis structures, I would say, okay, fluorine has 7 available valence electrons. Okay, I know that because of its position on the periodic table. It's in group 17, which it has 7 valence electrons. There are 2 of them. So I have 14 valence electrons in order to satisfy both fluorine molecules. So I draw both fluorines and I connect them with a bond because this is a bonded substance. So I subtract 2. There are 2 that are there, and I have 12 electrons that are left. Okay, since I have 12 electrons that are left, I have to look and say, is that 12 electrons enough to distribute to these fluorine atoms? And I would say, okay, this fluorine needs 1, 2, 3, 4, 5, 6. And this fluorine needs 1, 2, 3, 4, 5, 6. So because of that, 12 valence electrons is enough to satisfy this, so this would be my Lewis structure. You'd have 3 pairs of electrons on each fluorine combined by, are connected with a single line representing a shared pair of electrons. So now let's go ahead and take a look at nitrogen, and then I'll give you the answers to the rest of them. Nitrogen is going to be a little bit different, and the reason why it's going to be a little bit different is because, well, when we look at it, you see that nitrogen should have 5 valence electrons, okay, because it's in group 15. 5 valence electrons, and I'm going to draw out nitrogen with the nitrogens connected to each other. So since there are 2 of them, that means I've got 10 electrons. I've already bonded 2 of them, so that leaves me with 8 electrons left. At this point, you should look at these 2 things and say, I only have 8 electrons to make everything satisfy the octet rule. And that's not really going to work very well. So I don't have enough to distribute them. I have what's called an electron deficit. There's not enough electrons to make each nitrogen satisfy the octet rule. So I'm going to have to draw a double bond. And when I do, I subtract 2. That means I have 6 electrons available. Now instead of each nitrogen wanting 6 electrons, now each nitrogen only needs 4. But I only have 6 available, so once again I still have a deficit. So I need to subtract another 2 by putting a third bond right there. And when I do that, I have 4 valence electrons that are left. Well, if you look at this, each nitrogen only needs a pair of electrons now. So it needs 1, 2, 1, 2, and there's my valence structure for nitrogen. So now let's go ahead and show you what the valence electron structures for carbon dioxide and for methane are, which is the CH4. And for CH4, you're going to have something that looks like this. And for carbon dioxide, you're going to have carbon, double bonded O, double bonded O. And then don't forget to put your pairs of electrons on the outside of the carbon dioxide. Okay, next we're going to take a look at the difference between empirical and molecular formula. Remember, a molecular formula is what it is. So for example, C2H6 right there is a particular substance. It's called ethane. Okay, so this is the molecular formula for ethane, but it is not the empirical formula. The empirical formula is the lowest combination. It's like the lowest common denominator in fractions. So since I can divide all of these by 2, that the empirical formula for this substance would be CH3, even though that's not what it is. So the empirical formula for ethane is CH3. The molecular formula for it is C2H6. So now it wants me to write the empirical formulas for the following. You should be able to recognize that molecule as glucose. And so when you do that, it would be CH2O. The next one would be NF2. And finally, you should be able to recognize that that one is already the empirical formula because it cannot be reduced anymore. C3H7, if I were to divide, by 3, 7 doesn't divide cleanly into 3. If I were to divide it by 7, 3 doesn't divide cleanly, so it doesn't work. So the answer is that is already an empirical formula. So now we look at combustion analysis. Okay, combustion analysis is a reaction, is where you are trying to take a substance and burn it to figure out what it is. In order for something to burn, it requires that you have oxygen, and what it produces as a result is carbon dioxide and water, where the carbon dioxide is the only source of carbon. So if for every 5 moles of carbon dioxide that are produced, there were 5 moles of carbon in the original sample. Same thing, water is the only source of the hydrogen. So you look at the number of hydrogens that are in water, and that will tell you how many hydrogens were in the substance. So it says, what is the empirical formula for something that is 40% carbon, 15% hydrogen, and 45% oxygen? And this is by mass. So whenever you do this, you pretend that it's 40 grams instead of 40%, 15 grams instead of 15%, and 45 grams instead of 45%. You divide it by the molar mass. The molar mass of carbon is 12, the molar mass of hydrogen is 1, and the molar mass of oxygen is 16. So now, when I take 40 and I divide it by 12, I get 3.33. When I take 15 and divide it by 1, I get 15. And when I take 45 and I divide it by 16, I get 2.8. So now you have to play with these numbers a little bit, because right now you can't have 3.33 carbons and you can't have 2.8 oxygens. So generally what you do is you divide by the lowest number, and this one is 2.8125. So I'm going to divide all of those by this, 2.8125. And when I do that, I'm going to get 1 oxygen, because 2.8125 divided by 2.8125 is 1. When I take 15 and divide it by 2.8125, I get 5.33. Okay, and then finally when I take 3.33 and divide by 2.8125, I get 1.184. So if you notice, that was not particularly helpful because I didn't get whole numbers. So now you've got to look at these numbers and say, okay, well, what's the easiest way that I can get this thing to be reasonably a whole number? And so you have to start to play with these numbers, and you have to say, okay, well, this doesn't really make a whole lot of sense. The examples that you'll have on the test are not going to be this confusing. They actually come out as whole numbers. But really what you should do here is you should start by saying, okay, if I multiply this by 3, I will get this thing to a whole number. But what I do to 1, I have to do to all of them. So now I have 3 oxygens. I have 3 times 5.33 is 16 hydrogens. And then finally I've got to say, okay, 3 times 1.184, and that gives me about 3.5, roughly 3.5 carbons. And I'm still at that point where carbon is still, it's not working for me. So I say, okay, what do I do to get carbon into a whole number? And so I'd have to multiply it by 2. And what I do to that, I have to do to everything. So what I end up with is I get something like carbon 7, H32, and then I would get oxygen 6. And if you look, this is an empirical formula, because I can't take one of these and divide them. Now, if you have numbers that are closer to deal with, like if this was like 2.9 or 2.95 or something like that, you could round that up to 3. That can be just a matter of division. But when we get numbers like 3.33, that's very clearly not a whole number. So it takes a little bit of practice, but as long as you generally show your work and you make your justification, you can get the right answer. The last one says a 5-gram sample of a hydrocarbon, carbon and hydrogen only, is combusted with 3.8 grams of water and 5.2 grams of hydrogen is produced. What is the empirical formula of the sample? So if you look, I get 3.8 grams of water. The only source of hydrogen in the product, or excuse me, what is produced is the hydrogen. So I'm going to take some hydrocarbon, X and Y. It says carbon and hydrogen only. I'm going to add some oxygen to it. I'm going to make carbon dioxide and water. Well, the only place that I'm going to get carbon from is in carbon dioxide. The only place that I'm going to get hydrogen from is the water. So when I take a look at this thing, I would say, okay, hydrogen. Okay, once I have the hydrogen, I would say, okay, H2, or 3.8 grams of H2O, and I would say 18 grams of H2O is 1 mole, and every 1 mole produces 2 moles of hydrogen. And so from this particular sample, I would have 3.8 grams divided by 18, and then times 2, and I would get 0.422 moles of hydrogen. Okay, now the next thing that I would do is I'd say, okay, I have 5.2 grams of carbon dioxide. If I have 5.2 grams of carbon dioxide, I would say 44 grams is 1 mole. And then for every 1 mole of carbon dioxide, I get 1 mole of carbon. So I would do 5.2 divided by 44. And when I do that, I get 0.118. So this gets a little bit tricky, but if you were to look at this thing and I were to compare those two, I would say that is pretty close to a 4-to-1 ratio, which means that for every carbon that I have to have approximately 4 hydrogens. It's actually like 3.5 or something along those lines. If you tried to decide this was 3.5, I wouldn't argue with you. So I would probably accept either the answer CH4 or C2H7, something that is close to both of those. So it's a little bit of an art, something you have to get used to as you're doing this, but CH4 and C2H7 are both very close. Okay. Next, this is predict the shapes of the molecules below. So I identify my central atom, and my central atom is the carbon, and I have 4 things that are around it. I have no leftover lone pairs of electrons, so what I would say is I would say that this thing is tetrahedral. Okay, you should be able to use the idea of how many bonds there are and how many lone pairs there are to figure out this thing is trigonal pyramidal. Trigonal pyramidal. This thing right here is linear, and this thing right here is trigonal bipyramidal. Okay, at this point, you can move on to your independent practice. If you still have any questions on how to do the independent practice, use this as notes, or you can see your teacher for additional help.